Welcome to another GC Basic demonstration. This is part 11 for the PIC18xxQ24 chip family. This is specific to that chip family, but it's a generic approach, so you can actually apply these insights into any of the chips that GC Basic supports. So, what are we on? Part 11. I2C operations, and this is discovery, and this is a crucial piece I say to everybody that you should do before trying to get I2C operating, because if you don't do discovery, you won't know if your bus is set up, and I'll go through what I mean by that in a moment. So do like and subscribe to the video, and give it a thumbs up and let it run all the way through. Thank you. So we're on 11, and we're just going to do a bit of discovery, bit of an insight, and then on 12 we'll actually look at a handful of different GLCD solutions, and I'll give you an insight into those as we go through. But this is very much focused on the educational piece. So what have I got? I got my software installed, my programmer, a chip obviously, 4 LEDs and a potentiometer, some switches, TTL, and a GLCD device. I've added that to it. Let's have a look at the board that I've got connected up. This is my desk cam. So look, I've got the chip here, the Q24 here. I've got a potentiometer here. I've got a row of LEDs, some switches, and they're all connected via flying leads at the back of this thing. You can't, slightly out of picture, it doesn't really matter. Programmers attached here. I'm using a PIC18xxQ24 today. We will use other programmers as we move forward. And as you can see, there's a GLCD sitting here operating on address 78. And what we're going to do is discover that. Now, what I've got connected up there for is some power to this little board I've got here, and 2 data lines, which I will go into, those orange and yellow ones. But you can see it's operating, and we'll cease the operation shortly. But I just wanted to show you that's the sort of thing we're going to go and do. Okay. So let's talk about I2C. So it uses 2 connections. Okay, it uses open collector, open drains, call them what you like, and they're pulled up with resistors, and those 2 are called the SDA and the SCL, and they typically voltage at somewhere between 5 volts and 3.3, but you can have many different voltages. So we have an SDA line and an SCL, which is the clock line. Let's have a look in here. For those, let me just zoom in. I think I can zoom in with my camera. If I zoom in here, not only do I know it's on address 78 because it's written on it, you can see SDA here on the right hand side, and then to its left the SCL, and I've got those connected. And if you look just over, you can just about make them out. There's 2 resistors pulling it up, and I'll show you that circuit in a moment. This is the hardware I've actually got laid out, and what I've added into here and for this particular video are these 2. So SCL and SDA, they are on port C4 and C3 respectively. And very importantly, this time you must have the VDDIO voltage applied. Let me look at that a bit deeper. So this is the chip, this is a PDIP, it doesn't really, or SOIC, it doesn't really matter what the shape is, this is the theory. I have got my 5 volt applied to here, that's VDD. You must apply voltage into VDDIO2. Why? Because we are using this domain here, this green domain, and that is called the VDDIO2. Look down here in green, that's where it is. So we are using that, so we must, if we use the green pins, we must apply power to VDDIO, and I am using these 2 here as my I2C circuit. And why is that? Because it says down here, look, that they are compatible. So that relates to that, and this relates to this. So you've got a bit of a, not a Venn diagram, but it could have been. So you need volts up here, volts here, and for those that remember, I've still got coming out of RC6, the TX, the transmit to my serial, and that's what we're going to look at. So your connectivity is critical. You must put the VDDIO2 circuitry up. So what have I got? You saw the device. It's got, oh, so sorry. It's got two lines attached, the SDA and the SCL, and they're pulled up by, I'm using 4.2K resistors. And I pulled those up to the VCC. VCC, VDD, same thing, remember. Okay, so that's the setup, all the hardware. So what are we trying to do with I2C? What we're trying to do is send out a packet or sequence. And that sequence is the green one, the start, and it goes through to the red one called the stop. And what we need to do is send it some information that has an address, and then we typically send it data, and it's lots of data, so that might want to say data ... because you could send a lot of data, and you can send data out like this. There's a similar one for reading or receiving, but it's essentially you go start, I2 send, you do a send with an address, and then you do data, and then you do a stop. And we're going to use that to discover this device on the bus. And if you didn't have a pull-up resistor, you didn't have a clock line, or something was wrong, you won't get a response because there are signals that happen. And those signals are when the start condition happens, there's a transition. The data line transitions from low to high whilst the clock line is high. And if those transitions don't happen, that signals the beginning of the communication, there's an error on the line, and we need to capture that, and we can then report that back to the user. And then when you send data, every time you send data, you should get an acknowledgement back, because that means that your slave device on the bus, in my case a GLCD, is actually happy with the data coming in. And if you get an acknowledgement, good. If you don't get one, then you've obviously got a problem, and you can deal with that. Then you can send data, and the same thing happens. You send the data out. As you clock the data out, you get the acknowledged back. And if you don't get an acknowledged back, you know there's a problem. And then finally, stop. There's another transition of the SDA, sorry, or the data line. When the clock is high, it goes low, and there's a condition that you can test. And we capture those in a set of commands that are very simple to use in GC Basic. So the start sequence, the IC send sequence, the address sequence, they come in very complicated diagrams. I wonder if I could find one. Have I got a data sheet that's open? Let me just see if I have a data sheet open. Oh, there's PIC info. Let's go into PIC info. Let's open up a data sheet. I want to have a quick look at a diagram inside the data sheet. I'm just going to cursor down to the section I'm interested in. Where's the section I'm interested in? This one here. There are diagrams that look like this. I'll get you one up. They look like this. Okay, bus timeout. Oh gosh. I'm just trying to find you one that's really nasty, that sort of scares people away. I've not a lot of luck here finding one for. Oh, there you go. That's a good one. 7-bit addressing. That's what we're using. This diagram here looks fantastic. You'd need to understand all this to make it work, but do you? Because we're going to give you 4 commands that actually simplify this diagram. So you don't need to have the detailed knowledge, because the library that you're going to be using actually has very simple command set. It has a start command, a send command, or receive, depending on what you've got, and a stop. And that's really all you need, because the library is doing the groundwork for you. So this complexity in here of setting the SDA, setting up the actual hardware for you, ensuring that you've set all the counters and you're testing the acknowledgement state and the buffers are empty, all that is done automatically within GC Basic with these 4 simple commands. And that's been done like that for 10 years, maybe longer, I don't know. So our goal is to do this. You're going to use some commands we've seen before, and what we're going to do is we're going to send out some hardware I2C commands. We're going to test for it, and if we see a response, we are going to put something on the screen like this, and it says there's 2 addresses sitting here. We know it's on 78 for receiving data because we saw it working. but there's also a read address on 79. And if it works correctly, then you should see them. And a if you have a memory device as well, you might get A0 in here, you might get A2 or maybe A2 in there. Yeah. If you have lots of devices on, you'll get lots of responses. That is goodness. If you don't get anything back or there's exclamation marks, then the source code will tell you what to go fix. The clock line might be missing or something else. But the crucial thing is to do this discovery before you try using an I2C device, because you need to make sure that the solution is working. It's not a library issue necessarily. It could be, but it's more likely to be you've forgotten to put a pull up or you've forgotten to do something in the circuit. So what we're going to do is look at some sample code. We are going to set the PPS for the I2C support ports. We're going to use the PPS we've got for USART. We're going to set up the I2C, review the code, and just see what happens. Okay, that's what we do. So, let me just shut that, and I will shut down the whole editor. So, Control B, and I'm going to open up program 170. I did mention some of the GLCD. There they all are. What 80, 90, 200, 210, 220. We're going to rip through those in the next video to see how they all work in different ways. Okay, all right. Show serial I2C devices to serial terminal. That implies I've got a serial terminal. Okay, great. Let me zoom in on that for you. Great, there we go. So today's date is December the 1st. That's great. So I've got my standard header here about my chip, which is Q24 running at 64 megahertz. And I will walk you through it as we've done in the past. So let's have a look at the hardware. So the hardware, as I said previously, is on port C, and these are comments. These are commentaries. So I'm developing this diagram as we add more capabilities. We've seen all the other stuff before about LEDs and potentiometers and reset switches, etc. And then I've got a new piece here, which is around defining the I2C settings. And there are only a handful that are really needed. You need to tell the library which is your data port. And as I said up above, I'm using C.4 for my data, and for my clock or SCL, I'm using C3. So you just need to define two constants, data and clock there. And the H stands for hardware. And there's a software one as well. A very similar library, which actually is fully portable because you're not constrained to the hardware. So this requires that H at the beginning requires a module inside the chip that actually works. Then I'm telling it what baud rate I want to use, 100 kilohertz. And then I'd have to say, what is it? What mode am I in? I squared mode, and I'm a master. I could be a slave. And there's a whole series of demonstrations on how you can make a robust slave. But this isn't good enough, just setting these two, because I've got to set the PPS up. And so I've gone through and I've set up the PPS at the top as before, and we'll go through that. This is the serial, which we've seen before. And here is the PPS for as you can see, the clock SCL, that's serial clock line. Number one, I think there's two of these on here. This is for number one. And these are the two that are required to set up the clock, and these are the two that are required to set up the data line, or SDA. And you can use PPS tool or MCC to do that. You don't need to be a rocket scientist. You can paste those in yourself. Just make sure that they are set up correct. And at the moment, I would stay on RC3 and RC4 because that's my advice. Okay, the rest of it, I am not overly interested in, to be honest, because there are some other things down here which are specific controls for the Q20 and the Q24 that we're working at. I have a buffer size that's normally set to 128. I've set it to 16, and I'm muting a warning. That's just the setup. Let's look at the main program. Lots of strings in here being sent to the serial port. Look, hardware serial print. Where's the meat in this? Look, it says here, look, there's a 4 next loop from 0. I'll change that so that we can. We don't need to do it in hexadecimal. We can do it in decimal to 255. It's going to send out the following. The first time it comes through, it's set to 0. Send out start. Send out a byte with the address. Send out a 0, and then stop. And then we can test to see if this variable ACPOL state is false. If it's false, then we know that it's good. That means that the chip has responded. That's the chip. The I2C device has responded. And then I can actually show that on the screen. If not, 2 dashes. So it will go number 1 as the device ID, number 2, 3, 4, and eventually it will get to 78 hex, whatever that number is in decimal, which is 120. So it will go send out start, send out a byte, which is the address of 120, 78 hex, send out a 0, and then a stop. And it will then respond. It will say ACPOL state is false. Great, put it on the screen. So if I program that, function key F5, the chip down here will stop working because we've overwritten it. But if I bring up a terminal into the screen, we will see that I have not got my serial connected. No, it's not connected because I've been moving the bench around here today. A bit of a tidy up. I'm just connecting the serial. I'm just going to press the reset button, not the reset, let me just see what I've connect. Oh, there we go, perfect. It's now operating as expected. It runs it every time I push the switch. It's because my serial line was off the back. You can see that the GLCD is not operating. Let's just get rid of that because that's a bit confusing. Is that the screen we were on before? Is that the one we were on before? I think that's the one. It says 79 in here. So that means it's found a write address on address 78 and a read address on 79. That means that this works. And every time I push the button, magic happens. Now, what I've got hooked up into my machine is another computer. Oh, I've disconnected it. I had a Pro Ball set up, but it doesn't matter. Essentially, this is the important part of this video. You need to get a response back from your bus. Then the bus needs to say that it's happy. If I disconnected something, I'll disconnect. Which one? I'll take off the clock line. I've taken the clock line off. The program responds with nothing, as it quite rightly should, because there's nothing operating. Let me just push the button again. Nothing. I'm going to reattach the clock. You can't see me doing this. Bit of a mess. As I reattach the clock, I get a signal. If I disconnect, I'll try and do that over here. If I disconnect the data line, nothing. So it tells you there's a problem. I'm going to reconnect the data line on the little PCB here. That's my serial connection come off again. We get the bus come back. It's essential you do this test. If I didn't have the pull-ups, how can I test? If I take off the pull-ups, I can quickly take the pull-ups off. It's using the internal pull-ups, so that's interesting. Let me just take that off. I'll just see what's happening here. It's using the. There we go. So what I wanted to do there was put some volts back on there before I damage this GLCD. One moment. I'm really struggling to get that back on. There we go, back on. It's perfect, and it's robust, meaning it does it every time. And you will find that if you wanted to use the software option, which I'm going to show you now, that is also available. I'll show you where that is. So here we have back in the IDE. I'm just going to shut down that bottom window for us and get rid of that. Control J. Here we go. If I open up a folder in your demonstration folder, let me have a look in your demonstration folder. I'll zoom in on this for you so I don't have to struggle. If you zoom in on demonstration sources and you zoom in on I2C in your folder, I will zoom in a bit more. How about that? There we go, I2C. I2C, I2C Discovery, which is the top one, not the bottom one. That's I2C2, the second channel. At the top, you can see that I have posted in here a Q24 demonstration. I'll just bring that into view. Here is a I2C software discovery to terminal. Open that up. I've just put that inside of the IDE, as you can see. Now, interestingly, is software. Now, in the software one, what is interesting is that I only need the PPS for the USART, the configuration of the software I2C is via these four constants. You tell it what line's got the data, what line's got the clock. You might, and you should always disable the interrupts unless you know what you're doing, and your mode is a constant this time. And the rest of the program is essentially the same. I do a start, ascend, and a stop. So if I program that, it will fail. I will show you why. It's found the chip, and it now says software I2C on the terminal. Software I2C. Let me just do this. Unpower the whole board, power it back up, and it finds it. That's because the PPS needs to be unset when you're using the software option. You don't set the PPS. If you set the PPS in the software modules, it will fail. So you must reset when you've had a PPS set. You either set it to 0 in your program or you reset the hardware, which I just did. So we've now seen we can do software discovery of I2C and hardware discovery of I2C. Fantastic, works great. That's what I wanted to show you. So the next video is a set of videos just showing the capabilities of what we can actually do, some of the basic stuff, and I'll go through that in the next video. Enjoy.